For most of human history, the universe felt predictable. The sky moved in familiar patterns. Stars rose and set. Planets wandered slowly against the constellations. Even when we didn't understand why, we believed the universe followed rules. In the 20th century, physics felt almost complete. Gravity had an equation. Light had a speed limit. Space and time were the stable stages on which reality unfolded. And then, quietly, something began to feel wrong. Not dramatically wrong, not obviously broken, just off. The first signs didn't come from cosmic disasters. They came from careful measurements, from astronomers doing what they'd always done, looking, recording, and comparing. They noticed that galaxies were moving in unexpected ways. According to everything we knew, stars at the outer edges of a galaxy should move more slowly than stars near the center. Gravity weakens with distance. That rule worked perfectly in our own solar system. But galaxies refused to obey. Stars far from the galactic center were moving way too fast. So fast, they should have flown off into space. And yet, the galaxies remained intact, rotating calmly, as if held together by something we couldn't see. At first, astronomers assumed it was an error. Bad measurements, faulty instruments, incomplete data. They rechecked everything. But the problem didn't go away. This was the first quiet crack in our understanding. Then came another. In the 1920s, Edwin Hubble discovered that distant galaxies were all moving away from us. The universe was expanding. This was shocking, but it actually fit within Einstein's equations of relativity. Space itself could stretch. For a while, this expansion felt understandable. Gravity, the force that pulls everything together, should be slowing it down over time. The universe should expand, but more and more slowly. That seemed reasonable. But decades later, when astronomers measured the expansion using distant supernovae, they found something impossible. The expansion wasn't slowing down, it was speeding up, accelerating. This should not be happening. According to gravity, matter attracts matter. The expansion should be fighting against a constant pull, not getting faster. And yet, the universe was doing exactly that. Once again, the first response was doubt. Something must be wrong with the data. It wasn't. Multiple independent teams confirmed the result. The universe was accelerating. Something unseen was pushing space apart. This invisible influence was given a name, dark energy. Not because it was understood, but because it wasn't. Around the same time, the mystery of the too fast galaxies deepened. The missing gravity holding them together was named dark matter. So now we had two enormous, invisible components of reality. By the end of the 20th century, physicists faced a startling realization. Everything we see, stars, planets, gas, and dust, makes up only a tiny fraction of the universe, roughly 5%. The rest was dark, not metaphorically, literally undetectable by light or any other means we had. This should have caused a crisis. It didn't, not really. Instead, the models were adjusted. Dark matter was added to the equations. Dark energy was included. Simulations improved. And for a while, it worked. The universe, on paper, made sense again. But nature hadn't finished speaking. As our telescopes became more powerful, new anomalies appeared. Galaxies forming much earlier in the universe's history than expected. Black holes growing far too large, far too fast. Huge cosmic structures appearing before physics said they should have had time to exist. The James Webb Space Telescope has only intensified this discomfort. It looked further back in time than any instrument before it, and what it saw was not a gentle, gradual universe coming into being. It saw maturity way too early. Galaxies with defined, complex structures when the universe was still an infant. Stars forming with astonishing efficiency. Black holes that were already massive when they should have just been getting started. And once again, scientists questioned the data. And once again, the data held up. This pattern kept repeating. Measure something new. Discover a discrepancy. Try to explain it. Fail to fully resolve it. The universe wasn't misbehaving randomly. It was consistently violating our expectations. And that consistency is what matters. It suggests that the problem isn't just noise in the data. It's not a coincidence. It's not an error. The problem is our understanding. For centuries, we'd assumed that the laws of physics we discovered were universal and complete. That if we knew the equations, we knew the universe. But what if those equations are just approximations? What if they work well in our local neighborhood, but not across vast cosmic distances? They are empirical. They come directly from observation, from light captured by mirrors floating in space, from data streams measured with incredible precision. The universe isn't hiding its secrets maliciously. It's revealing them patiently, but only to those willing to notice the discrepancies. There's a common misconception that science advances through dramatic, sudden revolutions from singular geniuses. In reality, science advances through discomfort. An uneasy feeling that something fundamental is missing from our picture of the cosmos, or misunderstood, or was assumed too quickly. When a scientist says, "We don't know," it doesn't mean ignorance. It means honesty. And honesty is where real discovery begins. This series isn't about rejecting modern physics. It's about listening to it more carefully. It's about following the data wherever it leads, even when it leads away from comfort, even when it challenges our deepest intuitions, and even when it suggests that the universe is far stranger than we ever imagined. Over the next few videos, we're going to explore these cracks in our cosmic model, not to frighten or overwhelm you, but to understand them slowly, calmly, thoughtfully, because the universe doesn't demand urgency. It invites patience. And if we listen long enough, it begins to tell a new story. A story that starts with one simple realization. The universe we thought we knew was not ready for what we were about to discover. Thanks for watching. If you're ready to explore the frontiers of cosmology with us, make sure you subscribe and turn on notifications so you don't miss the next part of our journey. See you then. Have you ever looked up at the night sky and felt a sense of wonder? It's vast, it's beautiful, and it's full of stars. But what if I told you that everything you see, every star, every galaxy, every glowing nebula, is just a tiny fraction of what's actually out there? The truth is, the universe is hiding a secret. A deep, dark secret. It all started when scientists noticed something was wrong. Seriously wrong. Galaxies were spinning way too fast. So fast they should have torn themselves apart. Clusters of galaxies were sticking together when, by all rights, they should have flown off in every direction. It was as if an invisible hand was holding the cosmos together. At first, this was a tough pill to swallow. For centuries, astronomy was the science of light. We studied things because they shone. But now, gravity itself was telling us that light was lying. not on purpose, but by leaving out the most important part of the story. Astronomers measured how fast the galaxies inside were moving and found the same problem they saw with single galaxies, but on a colossal scale. The universe is filled with a type of matter that doesn't interact with light at all. It doesn't shine, it doesn't reflect, it doesn't cast a shadow. It sails right through normal matter, right through you and me, as if we're ghosts. But it has mass, and its gravity shapes everything. They gave it a practical, no-nonsense name: dark matter. It described what it wasn't: not bright, not visible. Now, scientists don't just invent new things for fun. They're a conservative bunch. They tried everything to explain these observations with the stuff we already knew. Faint stars? Nope. Dead suns? Not enough of them. No, the evidence was overwhelming. Something entirely new was needed, and dark matter was the perfect fit. Suddenly, all the weirdness made sense. It explained why galaxies spin so fast. It explained why galaxy clusters hold together. It explained the bizarre patterns of gravitational lensing. When scientists plugged dark matter into their computer simulations of the universe, something magical happened. The models started to look just like the real cosmos. Vast filaments of matter formed with galaxies strung along them like pearls. Clusters of galaxies assembled naturally. Without dark matter, the simulated universe was just a smooth, boring mess. Dark matter was the invisible scaffolding upon which our entire universe was built. But just because we accept something exists doesn't mean we understand it. What is this stuff? Particle physicists came up with a whole zoo of potential candidates: WIMPs, axions, sterile neutrinos. Each had its own theoretical appeal, but none have been found. Scientists built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a stray dark matter particle bumping into an atom. They've been waiting and waiting. So far, nothing. Particle accelerators have smashed atoms together, looking for any sign of its creation. Still, nothing. This lack of detection is, frankly, a bit troubling. Dark matter is supposed to be all around us, making up most of the matter in the universe. And yet, it's completely elusive. But science has taught us to be patient. We once thought neutrinos had no mass, and that black holes were just a mathematical fantasy. History shows that today's mystery is often tomorrow's discovery. Still, the doubts linger, especially as our observations get better. We've found some galaxies that seem to have almost no dark matter, while others are almost entirely made of it. That's not what the simplest models predicted. But then came the bullet cluster. This was the smoking gun. It's actually two galaxy clusters that smashed into each other. The normal matter, mostly hot gas, collided, slowed down, and got stuck in the middle. But the dark matter, which we can map using gravitational lensing, just passed right through, completely unfazed. You can literally see the separation, the normal matter lagging behind, and the invisible dark matter surging ahead. This was powerful, convincing proof. Dark matter wasn't just a fudge factor in an equation. It was a real substance, behaving in its own strange, ghostly way. And yet, we still don't know what it is. This creates a strange tension. Our entire understanding of the cosmos is built on something we can't see, touch, or identify. It forced a profound shift in how we view reality. Reality isn't just what we can see with our eyes or our telescopes. Reality is what has an effect, what moves things, what shapes the universe. Dark matter taught us a humbling lesson. The cosmos doesn't care about our senses. It plays by its own rules, and we can only figure them out indirectly by observing the consequences. And this lesson was just the beginning. Because, as strange and mysterious as dark matter is, it was soon joined by something even weirder. Something called dark energy. If dark matter builds structures, dark energy threatens to tear them all down. It's an invisible influence that's not just changing what the universe contains, but controlling its ultimate fate. And that is a story for our next video. Thanks for watching. If you're as fascinated by the mysteries of the universe as I am, make sure to subscribe and hit that notification bell so you don't miss our next deep dive into the cosmos. See you next time. For most of the last century, astronomers pictured two possible endings for our universe. The first was an endless expansion, a slow, graceful coasting into infinity. The second was a dramatic collapse, a big crunch, where gravity would finally win, pulling everything back into a single point. It was a cosmic tug-of-war, with gravity on one side and the initial push of the Big Bang on the other. The big question was simple. Is there enough stuff, enough matter in the universe, to stop the expansion? Then we discovered dark matter, this invisible substance that outweighed everything we could see. But that didn't change the basic idea. More matter just meant more gravity. It meant the universe should be slowing down, decelerating. It felt right. It felt intuitive. And then, in the late 1990s, everything changed. Two separate teams of astronomers were looking at distant exploding stars called Type Ia supernova. Think of them as cosmic light bulbs. Because they always explode with nearly the same brightness, we can use them to measure vast distances across the universe. By looking at how bright they appeared, scientists could tell how far away they were. And by measuring their light's redshift, they could figure out how fast the universe was expanding at that point in its history. They were building a map of the universe's expansion over time. And they expected to see the expansion slowing down, but that's not what they found. The data was telling them something impossible. The expansion was speeding up. These distant supernovae were dimmer than they should have been, which meant they were farther away than predicted. The universe wasn't slowing down. It was accelerating. At first, nobody believed it. It had to be a mistake. They checked their math, their instruments, their assumptions, but the signal was real. The conclusion was unavoidable. Something was pushing the universe apart, overpowering the relentless pull of gravity. It was a discovery that shook the foundations of cosmology. An accelerating universe just felt wrong. To explain this bizarre phenomenon, scientists had to dust off an old idea, something Albert Einstein had cooked up and then discarded. Back in 1917, he added a cosmological constant to his equations to force the universe to be static, which was the prevailing belief at the time. When the expansion was discovered, Einstein supposedly called this his greatest blunder. But now, his blunder was making a comeback. Except this time, instead of holding the universe still, it was acting like an anti-gravity force, driving everything apart. This mysterious cause of acceleration was given a name, dark energy, just like dark matter. The name dark energy is really just a placeholder for our own ignorance. We know it's there, but we have no idea what it is. It doesn't glow. It doesn't clump together to form structures. It seems to be a fundamental property of space itself. And here's the weirdest part. As space expands, more of this dark energy just appears. It doesn't get diluted like regular matter. Its density stays constant. This makes it incredibly powerful on a cosmic scale. Today, our best estimates suggest dark energy makes up about 68% of the total energy density of the universe. Dark matter makes up another 27%. And everything we've ever seen, touched, or measured, all the stars, galaxies, planets, and people, makes up less than 5%. Think about that. We are a tiny cosmic minority, living in a universe dominated by two things we can't see and don't understand. So what is this stuff? In Einstein's theory of general relativity, not just mass, but also pressure, creates gravity. Normal, positive pressure pulls things together. But dark energy has negative pressure. It pushes things apart. It's not a force acting within space, but a property that stretches the very fabric of space-time itself. As the universe expands, dark energy's influence grows stronger, pushing galaxies farther and farther apart. This leads to some truly mind-bending and frankly unsettling futures. Eventually, galaxies outside our local group will be pushed so far away, so fast, that their light will never be able to reach us. They will disappear beyond our cosmic horizon. The night sky will slowly grow darker and emptier. Future astronomers might look up and see only our own galaxy in a vast, static void. The very evidence for the Big Bang and the expansion of the universe will be erased. Dark energy isn't just changing the fate of the universe, it's changing what can ever be known about it. This whole idea presents a massive problem for physics. Our best theory of particle physics, quantum field theory, actually predicts that empty space should have energy, something called vacuum energy. The problem is, when we calculate how much energy there should be, the number is catastrophically wrong. It's off by a factor of 10 to the power of 120. That is the single worst prediction in the history of science. It's like measuring the length of a football field and getting an answer larger than the entire observable universe. No one knows why our theories fail so spectacularly here. So, is dark energy a constant, unchanging force? Does it evolve over time, perhaps growing stronger or weaker? Or is our understanding of gravity itself wrong on the largest scales? There are theories of modified gravity that try to explain acceleration without needing dark energy, but so far, none of them fully work. Dark energy remains a giant question mark, a symbol of how much we still have to learn. Its effects, however, are undeniable. It's the master of cosmic destiny. If it stays constant, the universe will expand forever into a cold, dark, empty state known as a heat death. If it grows stronger, it could lead to a big rip, tearing apart galaxies, stars, planets, and even the atoms that make us up. And if it weakens, gravity could one day take over again, leading to that big crunch we once imagined. We just don't know. What's so eerie about dark energy is its silence. Dark matter, for all its mystery, at least interacts through gravity. We can see its effects on the rotation of galaxies and the bending of light, but dark energy, it reveals itself only through the large-scale expansion of the universe as a whole. It's uniform, it's everywhere, and it's completely unavoidable. Together, Dark matter and dark energy have completely reshaped our view of the cosmos. Our universe is not the one we thought it was. The cosmos is dominated by the unknown, forcing a new sense of humility upon us. We had to admit that our cosmic inventory was woefully incomplete, but the story doesn't end there. As astronomers grappled with these two dark giants, they started noticing other strange things in their data. Subtle patterns on the largest scales, odd alignments in the cosmic microwave background, unusually large cold spots, hints that maybe, just maybe, our universe isn't quite as uniform and simple as we assume. This led to a profound question of cosmic coincidence. Why now? Why is it that today, in our specific cosmic era, the densities of dark energy and matter are roughly comparable? Why did acceleration kick in just as structures like galaxies were finishing their formation? These questions hint that there might be a deeper connection between them, a hidden rule in the cosmic playbook we haven't found yet. Or perhaps it points to something else entirely, something we haven't even begun to imagine. And that brings us to the next part of our story. Thanks for watching. If you're enjoying this journey into the mysteries of the cosmos, make sure to hit that subscribe button and join us for the next chapter. Before us, matter dominated everything. After us, dark energy will dominate completely, stretching everything out into infinity. This perfect balance doesn't last long on a cosmic timescale. It's a blink of an eye. And yet, here we are, witnessing it. This is famously known as the cosmic coincidence problem. Why do we observe the universe at this precise, special moment? Why not billions of years earlier, when matter ruled? Or trillions of years later, when dark energy has erased all the large-scale structures? Why now? At first, this just felt like a philosophical puzzle, but it quickly became a source of major scientific unease. Physics really doesn't like coincidences, especially ones of this magnitude. When two seemingly unrelated quantities, like the density of matter and the density of dark energy, happen to match up, scientists immediately suspect there's a hidden connection or a missing piece of the puzzle. You see, the density of dark energy seems to stay constant as the universe expands, but the density of matter gets diluted. So, the moment when they are equal happens only once, and it's very brief. This isn't something you'd expect from random chance. In other universes, dark energy might be too weak, and the universe might collapse back in on itself too quickly. Again, no observers. So, we naturally find ourselves existing in a universe that allows for complexity, a universe that allows for life to evolve. Therefore, the conditions we observe must be compatible with our own existence. For many, this explanation feels like giving up on finding a real physical reason, but it can't be dismissed entirely. Modern physics is increasingly pointing toward the idea of a multiverse, of vast, perhaps infinite, collection of universes, each with slightly different physical laws and constants. If the multiverse is real, then our universe might just be one of the rare, hospitable ones. The cosmic coincidence would then be a matter of selection, not some profound design or miracle. We won the cosmic lottery, so to speak. Still, many physicists resist this conclusion. They're holding out for a deeper law, a fundamental reason, not just a statistical outcome. And this scientific unease only grew stronger as our observations got better. Large-scale surveys of the cosmos, started to reveal subtle anomalies, strange patterns that shouldn't really exist in a perfectly uniform universe. We saw odd alignments in the cosmic microwave background, the afterglow of the Big Bang, unexpectedly large cold spots, even hints of preferred directions in the cosmos. At first, these were mostly dismissed as statistical flukes, noise in the instruments, or contamination from our own galaxy. But some of them have persisted through multiple experiments. The universe appears the same in all directions on the largest scales, but maybe not perfectly so. There were hints of structure beyond what our standard models predicted. These anomalies were tiny, but their persistence was troubling, and they tended to cluster at the very largest observable scales, the exact place where it's hardest to be certain about anything. This led to some wild speculation. What if our most basic assumptions are wrong? What if the cosmological principle, the foundational idea that the universe looks the same from everywhere and in every direction, is only an approximation? Maybe we live in a region of space that's different from the average, affecting what we see. These theories try to get rid of the need for dark energy by changing the laws of gravity. So far, none have managed to replace our standard model, but the search continues. Dark energy is forcing us to reevaluate our understanding of gravity itself. But there's an even deeper source of unease. Dark energy doesn't just affect the future, it affects the very nature of causality. As the expansion accelerates, distant regions of the universe move away from us faster than the speed of light. This means they become causally disconnected from us. Information from those regions is lost forever, not destroyed, but simply unreachable. This creates cosmic horizons, ultimate limits to what we can ever observe. Our observable universe, the part we can see, is effectively shrinking relative to the whole. The universe is becoming increasingly isolated, with each gravitationally bound system, like our local group of galaxies, becoming its own lonely island in a vast, empty ocean. The long-term fate of the universe becomes quiet, cold, and empty, but also, in a way, simple. Complexity fades away. Structure dissolves. Dark energy isn't violent. It's a gentle, relentless, silent force. It's your perspective. The universe isn't a static, timeless stage. It evolves, and we are deeply embedded within that evolution. Dark energy forces us to confront our own limitations, not just of our lives, but of our knowledge itself. There are questions that future observers, trillions of years from now, will never even be able to ask, because the evidence will have been stretched beyond their cosmic horizon. We live during a privileged, fleeting epoch, where the universe still reveals its past. This might not be comforting, but it is humbling. For all of human history, our understanding of the universe came through light. First, the light our eyes could see. Then, we built instruments to see other kinds of light: radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each new window we opened on the cosmos showed us something new, something unexpected. But all of them had one fundamental limitation: they needed matter to glow. For us to see anything, a star had to shine, gas had to heat up, or particles had to radiate energy. If something was completely dark, it was completely invisible. We were blind to it. Then, in the early 21st century, everything changed. The universe gave us a new sense, not sight, but something more like hearing. In 2015, incredibly sensitive detectors on Earth felt a tiny, faint disturbance, a ripple. But this wasn't a ripple in air or water. It was a ripple in the fabric of space-time itself. More than 1 billion years ago, in a galaxy far, far away, 2 black holes had been spiraling around each other. As they got closer and faster, they eventually smashed together and merged. Albert Einstein had predicted they existed 100 years earlier, and now, finally, we had heard them. It was a historic moment, not just because it proved Einstein right again, but because it signaled a revolution. Astronomy had changed forever. We were no longer limited to light. We could now listen to the universe. They pass straight through clouds of dust, through gas, through entire galaxies. Practically nothing can stop them. This means they carry information about cosmic events that light could never show us. The merger of 2 black holes, for instance, releases almost no light. Before 2015, these events were theoretical, invisible ghosts. Now, we could hear them. In their own quiet, gravitational way, they were loud. Every detection tells a story. We can hear the soundtrack of 2 massive objects spiraling together, faster and closer, until space-time itself rings like a bell. The shape of that signal, that chirp, tells us everything. It encodes the masses of the black holes, how they were spinning, and how far away they were. It's pure gravity, with no assumptions about light or matter needed, just the raw geometry of the cosmos. This kicked off a brand new era, gravitational wave astronomy. And right away, the universe started surprising us. The black holes we were detecting were much heavier than we expected. These mergers were happening far more often than our theories predicted. It seemed the universe was a more violent, more dynamic, and more restless place than we'd realized. But at the same time, it was also more orderly. The waves we detected matched the precise equations of Einstein's general relativity perfectly. They were clean, predictable, elegant. Gravity was speaking clearly. This incredible clarity pushes us to ask deeper questions. If space-time can ripple and wave, what exactly is space-time? Gravitational waves confirmed that space-time isn't just an abstract background. It's a real, physical thing. It can stretch, it can compress, it can oscillate, and it carries energy. Space-time behaves like something real, but it isn't matter. And it isn't energy in the way we usually think of it. It's dynamic geometry. And that geometry can store and carry information. Gravitational waves are information written directly onto the fabric of reality. This connects to a fascinating idea that, at its most fundamental level, reality might be made of information, not particles or fields, but relationships and changes. Gravitational waves also give us a brand new way to test gravity itself. So far, every single detection has been a perfect match for Einstein's theory. No deviations, no surprises. This makes us more confident than ever in general relativity. But it also creates tension, because general relativity doesn't get along with our other pillar of modern physics, quantum mechanics. Gravity remains stubbornly classical, non-quantum. Some physicists had hoped that gravitational waves might show us tiny cracks in Einstein's theory, hints of quantum gravity or extra dimensions. So far, they haven't, but we've only just started listening. This new sense also lets us probe the very beginning of the universe. The earliest light we can see, the cosmic microwave background, comes from about 380,000 years after the Big Bang. Before that, the universe was a hot, dense soup, completely opaque to light. But gravitational waves don't care about opaque. They could carry information from much, much earlier, perhaps even from the first trillionth of a second after the Big Bang, during a period called cosmic inflation. Detecting these primordial gravitational waves is one of the ultimate goals of modern cosmology. It would be direct evidence of inflation and would connect quantum mechanics, gravity, and cosmology in a single, beautiful observation. And there's more. When two neutron stars collide, they create both gravitational waves and a flash of light. This gives us a completely independent way to measure cosmic distances, what astronomers call a standard siren. This is incredibly important because right now there's a huge debate in cosmology. Different methods for measuring how fast the universe is expanding are giving different answers. This disagreement might be pointing toward brand new physics. Gravitational waves offer a clean way to help settle this debate. All of this has revealed something almost poetic. The universe is constantly ringing. Black holes and neutron stars are merging all the time, all across cosmic history. Most are too weak to detect one by one, but together they form a constant background hum, a cosmic murmur. Listening to this background would be like hearing the entire history of the universe compressed into a single sound. The universe is not a silent, empty place. It is quietly, ceaselessly active. This also changes how we might find the most mysterious stuff in the cosmos, dark matter. It's called dark because it doesn't interact with light, but it has mass. And anything with mass that moves and accelerates creates gravitational waves. So if dark matter forms clumps or exotic objects that merge, we might be able to hear them. Gravitational waves could finally give us access to the dark side of the universe. So far, no luck, but future detectors, like the space-based observatory LISA, will be thousands of times more sensitive. They will hear the slow dance of supermassive black holes at the centers of galaxies, and maybe, just maybe, things we can't even imagine yet. This leads to a profound shift in perspective. The universe isn't just a collection of objects sitting in a static box. It's a dynamic, interconnected process. Space-time isn't the stage, it's one of the main actors. This blurs the line between matter and space, between the container and what's inside. They are two sides of the same coin, and we are part of it. Our own bodies, tiny as they are, bend space-time around them. Every move we make sends out infinitesimal gravitational waves. We are not just looking at the universe from the outside. We are participants, woven into its very fabric. Listening to gravitational waves is like listening to the universe talk to itself, about itself. It's a quiet conversation, that has been going on for over 13 billion years. We have only just learned how to eavesdrop, and what it's telling us is that the universe is richer, more subtle, and more interconnected than we ever dreamed. But it also hints at a distant future. These cosmic collisions, these waves, they all radiate energy away. Over unimaginable timescales, the universe will grow quieter, the waves will fade, the cosmic symphony will dwindle to silence. This makes us wonder, is this the final act? Or is there another movement yet to come, a cycle of rebirth we can't yet foresee? For now, all we can do is keep listening to the quiet whispers of space-time. Thanks for watching. For a while now, physics has been at a strange crossroads. The math works, our predictions match what we see, and technology keeps getting better. Yet, something feels missing. The universe seems to be playing by a set of rules, much deeper than just matter and energy. We see patterns everywhere. Symmetries repeat themselves from the tiniest particles to the largest galaxies. The same mathematical structures just keep showing up. This leads to a wild possibility. What if matter isn't the most basic thing? What if space-time itself isn't fundamental? What if the universe, at its very core, is made of information? This idea didn't come from philosophy. It came straight from physics. The big turning point was black holes. When physicists looked at black holes closely, they found a paradox. General relativity says anything that falls into a black hole is gone forever. All its information just vanishes. But quantum mechanics says, no way. In quantum theory, information can never be destroyed. It can get scrambled or change form, but it can't just disappear. This was a huge problem. Either general relativity was incomplete, quantum mechanics was wrong, or maybe both were. Stephen Hawking made things even more complicated. He showed that black holes aren't totally black. They give off a faint glow of radiation. Very slowly, over unimaginable amounts of time, they evaporate. This radiation seems completely random. So, if a black hole evaporates completely, what happens to the information of everything that fell inside? If it's gone, quantum mechanics is broken. If it gets out, how? This became the famous black hole information paradox. After decades of intense debate, a surprising answer started to take shape. The information isn't lost, but it's not stored where you'd think. This led to a truly radical concept, the holographic principle. Think of a hologram, where a two-dimensional surface creates a three-dimensional image. At first, this sounded crazy, but the math backed it up. It's like temperature. Temperature is real. You can feel it, but it emerges from the collective motion of countless tiny particles. This changes everything. Space isn't a stage, and time isn't a clock ticking in the background. They are outcomes, consequences, derived from something deeper. Entanglement is that weird quantum connection where two particles share a state. What happens to one instantly affects the other, no matter how far apart they are. Some physicists now think that spacetime is literally woven from these threads of entanglement. The geometry of space is just a reflection of the patterns of information shared between its parts. This isn't just a fun idea, it's supported by concrete math. When you change the entanglement patterns, space-time geometry changes. If you remove the entanglement, space-time itself collapses. This suggests that reality is less like a giant machine and more like a vast computation. Not a computer simulation like in the movies, but a relational structure where information is what defines existence. This connects right back to cosmology. If space-time emerges, then the Big Bang might not have been a beginning. The rapid inflation of the early universe might have been a massive reorganization of entanglement. Dark energy and dark matter might be emergent effects of this informational reality. These ideas are definitely speculative, but they aren't just random guesses. They pop up naturally when we push our current theories to their absolute limits. The universe acts like a system that conserves one thing above all else: information, not energy, not matter, but information. And this has serious consequences. If information is fundamental, then observation matters. The act of measuring something matters. Quantum mechanics has been telling us this for a century. Observers aren't just passive onlookers. They're part of the system. Reality isn't fully defined until it's measured. This is unsettling because it blurs the line between the observer and the observed, between mind and the universe. Physics has tried to avoid these questions for a long time, but modern theories are forcing them back into the light, not as philosophy, but as math. Cosmology is now asking questions that sound philosophical but demand scientific answers. What is space? What is time? What is information? What does it even mean for something to exist? These aren't just abstract thoughts. If space-time is emergent, then at the smallest possible scales, the universe might not be smooth and continuous. It might be discrete, pixelated, made of fundamental units of information. Below this resolution of reality, at the so-called Planck scale, concepts like distance and location would lose their meaning. This also messes with our idea of causality. If space-time emerges, then cause and effect might not be fundamental either. They could be byproducts of deeper rules that govern how information flows. We experience time as a river, always flowing forward. But time itself might just be a kind of cosmic bookkeeping, a way for the universe to order the updates to its information. The universe might not be evolving asterisk in asterisk time. Time might be emerging asterisk from asterisk, that evolution. If time emerges, then the universe didn't begin asterisk in asterisk time. Time began asterisk with asterisk the universe, or more accurately, with the emergence of the space-time we know. Before that, the word before has no meaning. This solves some paradoxes, but creates new ones. Why does it only seem to move forward? Why does entropy or disorder always increase? The arrow of time remains one of the deepest mysteries in all of physics. It connects thermodynamics, cosmology, and information. Entropy is really just a measure of missing information. The arrow of time points toward increasing entropy, increasing disorder, and increasing uncertainty. As systems interact, entanglement increases, and this creates a one-way street, a direction. This picture is elegant, but it's still incomplete. It hints at something profound. The universe might be less like a thing and more like a process. This perspective is unsettling, but it's also unifying. It suggests the universe isn't just an indifferent machine. If reality is information, then the laws of physics themselves might not be absolute. They might just be stable patterns, reliable habits of the universe, but not eternal and unchanging. They might emerge and even evolve, just like space and time. And that raises a terrifying question. Could the laws of physics themselves change? Not overnight, but slowly, subtly, over cosmic ages. If so, then the universe isn't governed by fixed rules, but is guided by evolving principles. And that would mean everything we think we know today is just a snapshot, a temporary truth. This possibility pushes cosmology to its absolute edge, where certainty fades and humility returns. To explore this idea, physicists turned back to observation, looking for tiny signs that the constants of nature might not be so constant after all. Signs that the universe is not static, even in its rules. That journey continues in our next video. Thanks for watching. If you found your brain slightly melted in the best way possible, hit that like button and subscribe for more deep dives into the cosmos. See you next time. For centuries, physics rested on a quiet assumption. The laws of nature are permanent. Gravity today is the same gravity that shaped the first stars. Electromagnetism behaves now as it always has. The constants of nature are just that constant. This feels obvious. Without it, science would collapse, predictions would lose their meaning, and experiments wouldn't generalize. But modern cosmology has a way of unsettling even our most basic assumptions. Because when scientists began looking closely enough, even the laws themselves started to look less rigid than we thought. It all began cautiously, with extreme precision. Physicists measured fundamental constants with incredible care: the speed of light, the charge of the electron, the strength of the electromagnetic force. These are the numbers that define reality. If you change them even slightly, chemistry fails, stars don't form, and life as we know it becomes impossible. For a long time, Every measurement confirmed their stability. No change. But then, at the very edges of observation, strange hints appeared. Some astronomers, studying distant quasars' light that had traveled for billions of years, noticed tiny shifts in their spectral lines. At first, this was blamed on equipment errors or intervening gas clouds. But as more and more data accumulated, a pattern started to emerge. The fine structure constant, which governs the strength of electromagnetic interactions, appeared to be slightly different in different directions of the sky. The variations were tiny, almost negligible, but they were consistent enough to raise eyebrows. If this is true, it's revolutionary. It would mean that physical laws are not the same everywhere, or perhaps not the same always. Either possibility is deeply unsettling. Physicists reacted with caution. Extraordinary claims require extraordinary evidence. Independent teams reanalyzed the data. Some found no variation at all, while others found similar hints. The results remain controversial, with no definitive conclusion yet. But the question is now officially on the table. Could the constants of nature vary across space or time? If they can, what does that even mean? One possibility is that these constants are like fields, similar to temperature or pressure. They just have values that can change from place to place. In this view, the laws we observe are just our local conditions, not universal absolutes. This idea aligns uncomfortably well with some of our most advanced theories. In string theory, for example, the constants aren't fixed. They depend on the configuration of extra, hidden dimensions. Different configurations lead to different physics. The theory naturally predicts a vast landscape of possible universes, each with its own set of laws. Our universe would be just one of them, not unique, just the one we happen to observe. If constants do vary, then cosmic history becomes far more complex. The early universe might have obeyed slightly different rules. The way structures like galaxies formed could be different. Even the fundamental arrow of time could behave in another way. But if the laws can vary so much, why are they so incredibly stable right here, right now? We see consistency over billions of years. Perhaps the variations are extremely slow, or maybe they only occur across vast cosmic scales. Or maybe we just happen to live in a particularly calm, uniform region of the cosmos. And here, that old idea comes back, the anthropic principle. We observe stable laws because regions with unstable laws can't host observers like us. This explanation can feel unsatisfying, but it's becoming harder and harder to dismiss, because physics keeps pointing toward flexibility, not rigidity. Another line of evidence comes from something called symmetry breaking. In the ultra-hot, ultra-dense early universe, the fundamental forces of nature were unified. As the universe cooled, these symmetries broke, the forces separated, and their properties became distinct. The laws changed, not in their fundamental form, but in how they manifested. This already tells us that laws evolve in a certain sense. What we call laws might just be emergent behaviors, like the rules of fluid dynamics. Those rules work perfectly for a river, but they break down at the molecular level. Perhaps the fundamental laws of physics are similar, effective, approximate, and dependent on context. This idea deeply unsettles the classical view of physics, but it fits the modern evidence. Quantum mechanics is probabilistic, not deterministic. General relativity describes a smooth spacetime, while quantum theory suggests it's made of discrete units. Both theories work beautifully, but neither is complete. Reality seems to accommodate multiple descriptions, depending on the scale you're looking at. So, maybe the laws aren't written into the fabric of the universe, like commandments. Maybe they arise from deeper, more fundamental principles that are informational, relational, and statistical. If so, then what we call constants are just equilibrium value stable patterns that have emerged from a vast space of possibilities. This makes the universe less like a perfect, rigid machine and more like a complex, self-organizing system. It's adaptive and stable, but not frozen. This perspective completely reframes cosmology. The universe isn't just governed by a set of eternal decrees. It evolves not just in its content, but in its very structure and, possibly, its rules. This has a profound implication for prediction. We can predict what will happen within a certain era or a certain regime, but we can't predict things absolutely. The future may obey slightly different rules than the past. Not enough to break the continuity of reality, but just enough to alter its ultimate destiny. Dark energy might be a perfect example of this. Its dominance in the cosmos only emerged relatively recently in cosmic terms. Its origin might be tied to the evolving properties of the vacuum of space. Perhaps what we call dark energy is just the universe adjusting itself, following some deeper rule we don't yet understand. This also changes how we think about the fine-tuning problem. If constants can vary across a multiverse, then our finely tuned universe is just a matter of selection. If constants evolve over time, then fine-tuning is a product of history. Either way, it's not a random accident. It's a form of structure, but not design in the classical sense. It's more like a statistical necessity patterns emerging from an immense space of possibilities. This is an uncomfortable thought because it removes certainty. It removes finality. There may be no single, final theory of everything, only deeper and deeper approximations and better frameworks. Physics becomes less about uncovering ultimate truths and more about mapping the islands of stability in the cosmic ocean, understanding why certain patterns persist and why the universe looks so hospitable to us right now, but not always and not forever. This shift also affects how we think about meaning. If the laws themselves evolve, then purpose isn't built into the universe from the start. But it's not pure randomness either. The universe isn't chaotic. It's structured, just not frozen. This is a subtle but profound idea. It mirrors our own experience. Human laws evolve, cultures evolve, languages evolve. Yet, through it all, patterns persist, rules emerge, and stability arises. The universe might be doing something very similar, just on a cosmic scale, and this parallel might be more than just a metaphor. It could be literal. The universe may be a kind of computer, processing information, exploring its own possibility space, and settling into stable configurations. Observers like us arise in those pockets of stability where complexity can flourish. We aren't cosmically special, but we are rare, and we are temporary. This realization is sobering, but it's also grounding. It places humanity firmly within cosmic evolution, not as outside spectators of a finished show. We are witnessing a phase, a moment in time, and moments pass, which raises the final question. If the laws and constants can evolve, what is the ultimate fate of the universe? Not just in terms of expansion, but in terms of its complexity. Will it become simpler or more complex? Will consciousness vanish, or will it transform into something new? These questions are no longer just science fiction. They are the natural extensions of modern cosmology. Because once the laws are no longer absolute, the future multiplies into countless possibilities. Physics doesn't yet have the answer, but observation continues. Because despite all these theoretical uncertainties, the universe is still speaking to us through light, through structure, through motion, and recently, through something entirely new: ripples in space-time itself, gravitational waves. They gave us a new sense, a new way of listening to the cosmos. And what we heard began to change everything. Thank you so much for watching. If you enjoyed this journey to the edge of physics, be sure to like and subscribe for more. We'll continue this story in our next video. For centuries, our only way to study the universe was through light. We started with what our eyes could see, then built telescopes that could detect radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each new window we opened showed us something incredible and unexpected. But they all had one major limitation. They relied on things that glow. Stars had to shine, gas had to get hot, particles had to radiate. If something was completely dark, we were completely blind to it. Then, in the early 21st century, everything changed. The universe gave us a brand new sense, not sight, but hearing. In 2015, incredibly sensitive detectors here on Earth felt a tiny disturbance, a ripple, not in the air, not in light, but in the fabric of space-time itself. More than 1 billion years ago, two massive black holes had spiraled into each other and collided. Their violent merger sent waves pulsing outward at the speed of light. By the time these waves reached us, they were almost impossibly faint. They stretched and compressed space by a distance smaller than the width of a single proton. And yet, we detected them. This was the first direct detection of gravitational waves, a phenomenon predicted by Albert Einstein 100 years earlier. We had finally heard them. This moment was historic, and not just because it proved Einstein was right again. It was historic because astronomy itself was transformed forever. We were no longer chained to light. We could now listen to the cosmos. Gravitational waves don't care about darkness. They pass straight through dust clouds, gas, and entire galaxies, as if they're not even there. Nothing stops them. This means they carry information about cosmic events that light can never reveal. The merger of two black holes, for instance, emits almost no light. Before 2015, these events were invisible ghosts in the cosmic dark. Now, they were loud in their own quiet, gravitational way. Each detection tells a story. We can hear the tale of two massive objects spiraling closer and closer, faster and faster, until space-time itself rings like a bell. The signal we receive is incredibly pure. It encodes the masses of the objects, how they were spinning, and how far away they were. Their mergers were happening more often than we thought possible. These cosmic collisions were taking place in environments we hadn't anticipated. Is it a substance, a medium, or just a mathematical idea? Gravitational waves confirmed that space-time isn't just an abstract background. It has real, physical properties. It can stretch, compress, and oscillate. It carries energy. It behaves like a real thing. But it's not matter, and it's not energy in the usual sense. It's dynamic geometry. And that geometry can store and transmit information. This idea connects to a fascinating concept that reality itself might be informational at its core, not made of particles or fields, but of relationships and changes. Gravitational waves are a perfect example information encoded directly into the shape of spacetime. They also give us a brand new way to test gravity itself. So far, every single detection has perfectly matched the predictions of general relativity. No strange deviations, no weird surprises. This makes us more confident in Einstein's theory, but it also deepens a major puzzle in physics. General relativity, our theory of gravity, doesn't get along with quantum mechanics, our theory of everything else. Gravity remains stubbornly classical. We had hoped gravitational waves might show us some cracks in Einstein's theory, some hint of quantum gravity or extra dimensions. So far, they haven't, but we've only just started listening. Gravitational waves are also our best hope for peering into the universe's infancy. The earliest light we can see, the cosmic microwave background, comes from about 380,000 years after the Big Bang. Before that, the universe was a hot, dense fog, completely opaque to light. But gravitational waves don't have that problem. They could carry information from much, much earlier, perhaps even from the moment of inflation, the explosive expansion that kicked off the Big Bang. If we could detect these primordial gravitational waves, it would be one of the greatest discoveries in history. It would be direct proof of inflation and tell us about the quantum fluctuations of spacetime at the very beginning of time. This is one of the most ambitious goals in modern cosmology. Detecting them would connect quantum mechanics, gravity, and cosmology in a single breathtaking observation. It tells us that the universe is constantly ringing. Mergers are happening all the time, all across cosmic history. At this very moment, we are all floating in a sea of gravitational waves. Most are too weak to detect individually, but together they create a constant background hum, a cosmic murmur. Listening to this hum would be like hearing the entire history of the universe, every collision, every cosmic cataclysm compressed into a single sound. There's something strangely calming about knowing the universe isn't silent. It's quietly, constantly active. This new sense also democratizes our view of the cosmos. Gravitational waves treat all mass equally. They don't care if an object shines or not. Black holes, neutron stars, or even exotic objects we haven't imagined, yet if it has mass and it's moving, it creates ripples in spacetime. This means gravitational waves could finally reveal the dark universe. We might be able to detect dark matter not just by its indirect gravitational pull, but by watching it move, clump together, or even merge. So far, we haven't found anything definitive, but the potential is thrilling, and the technology is only getting better. Future observatories, like the space-based detector LISA, will be far more sensitive. They'll detect lower frequency waves from the mergers of supermassive black holes at the centers of galaxies, and maybe even from the dawn of time. We'll be listening to a full symphony of spacetime with notes that last from milliseconds to years. All of this leads to a beautiful realization. So, once scientists figured out the universe isn't just expanding, but speeding up, they had to ask a tough question. How does this all end? Not tomorrow, not in a billion years, but in the deepest, most distant future you can imagine. Suddenly, cosmology wasn't just about our origins. It became about our destiny. At first, the ideas were pretty straightforward. If gravity was strong enough, it could pull everything back together in a big crunch. If expansion was stronger, the universe would just keep growing forever. But then dark energy entered the picture, and it changed everything. Because acceleration that reshapes fate. The most widely accepted scenario today is called heat death. In this future, dark energy stays constant, and the expansion just keeps going. Galaxies drift further and further apart until they vanish from each other's view. Stars stop forming because the gas runs out. All energy will be evenly spread out, meaning no work can be done. It's the state of maximum entropy. This isn't a violent, explosive end. It's a quiet, slow fade to black. Everything just runs out, not with a bang, but with an endless, silent whisper. Complexity dissolves, structure vanishes, and even matter itself might not be permanent. If protons decay, everything dissolves into a thin soup of radiation. If not, black holes will be the last thing standing until they too disappear. Time will still pass, but nothing will ever happen again. But that's just one possibility. What if dark energy isn't constant? What if it gets stronger over time? That leads to a much more dramatic ending, the Big Rip. In this scenario, the repulsive force of dark energy grows so powerful it overcomes everything else. First, it would rip apart clusters of galaxies, then the galaxies themselves. Then it would tear solar systems apart, pulling planets away from their stars. It would get stronger and stronger until it could overcome the forces holding planets and even atoms together. In the final, terrifying moment, the very fabric of space-time itself would be torn to shreds. Now, this is pretty speculative. Our current observations don't really point to this, but they can't rule it out either. What if it's metastable, meaning it's stable for now, but could decay into something else in the future? If that happened, it could trigger a phase transition throughout the entire cosmos, like a pot of boiling water suddenly flash freezing. Anything caught inside this bubble would be instantly rewritten. Our universe would fundamentally change its nature. This isn't just science fiction. It's a real possibility based on quantum field theory. Our vacuum state might not be the most stable one. Of course, there are also the old ideas of a cyclic universe, one that goes through endless cycles of a big bang and a big crunch, a big bounce. Instead of starting from a single point, our universe might have bounced from a previous, contracting one. The light they emit will no longer be able to reach us, no matter how long we wait. They will disappear from our sky forever. Imagine, billions of years from now, future astronomers looking up. Their sky will be mostly dark and empty. They'll see the stars in our own local group of galaxies, but that's it. They won't see distant galaxies rushing away. They won't see the faint afterglow of the Big Bang. A cosmos fragmented into causally disconnected patches, each living out its own fate, unaware of the others. Is the end of interaction the end of existence? The universe doesn't need us to give it meaning. It just is. That's a cold, hard truth of cosmology. It doesn't promise comfort, it just promises understanding. But let's look at one final, bizarre idea. Even in a cold, empty universe, given infinite time, random quantum fluctuations could, just by chance, create complex things again. A Boltzmann brain. This idea is deeply disturbing and creates all sorts of paradoxes, but it forces scientists to question what it even means to be an observer.